Hello, assalamu alaikum everyone. I hope you all will be fine. Today I have already conducted this class via Zoom, but I have seen over there are very limited students present in the class, and even due to networking problem, I was unable to deliver the lecture properly and smoothly. So therefore, I'm going to record this lecture, and this will be uploaded on your Zoom on YouTube, right? So today our topic is to discuss about the electric flux, and you may know about the before electric flux we have discussed in detail about the electric field intensity, and also we have discussed about the geometrical interpretation of electric field intensity. I mean we have introduced the concept of electric field line, and that is totally an imaginary concept, right? And before electric field line we have discussed about the electric field intensity, which is one of the mathematical and quantitatively demonstration of electric field produced by the electric charge, and that was the concept which was given by Michael Faraday. Okay, so today we are going to discuss quantitatively how to measure the electric field lines, right? That is the main objective of today's lecture. Okay, how would you measure the electric field lines quantitatively? So for this we introduce concept of the electric flux. Okay, so in electric flux we are discussing just the in electric flux we are just discussing the we are going to discuss just the measurement of electric field line through vector area. So from this we concluded that for measurement of electric flux we need two things. We have to know about the electric flux, electric field intensity, and we have to know about the vector area. So these two things are important for quantitatively measurement of the electric flux. So first of all, I would like to say something about the vector area. Normally till to date we have familiar about that area is not a vector quantity, it is just a scalar quantity. But here we will consider this area as a vector area. So why we consider this as a vector area? So let me discuss some things over here. Actually, to measure the electric flux quantitatively, so this measurement of electric flux depends upon the orientation of the surface area with respect to electric field line. I mean if we have different orientations, so we will have different measurement of electric field lines. So in this regard we are going to associate the direction to the surface area. So in that sense we consider that area as a vector area. So now we are in the position to say that a vector area have two properties like a vector quantities, magnitudes as well as direction. So the magnitude means magnitude of a vector area is simply equivalent to the area of their surface, right? But for the direction we have to draw normal to that surface area. So that normal to the surface area will represent the direction of that vector area. So now the thing which is changing with respect to the electric field line, that is called the direction normal to the surface area. So here in this figure A there are two different surface areas are given. In the first one the normal is in upward direction, in the second one is the normal in the downward direction. So this clearly demonstrates that if the normal which drawn to the surface area is changing, the direction of surface area is also changing. So that's why that is called vector area. Okay, so now we are going to put this vector area in some external electric field in order to measure the electric field line quantitatively. So for the first case I am going to consider this surface area which makes some angle theta with respect to electric field line, which is not which is an arbitrary angle theta, right? It could have any values, right? This theta is not a specific one. I mean this is not 90, this is not 45, this could be arbitrary angles. I mean it could be any values, depends upon the situation. It could be perpendicular, it could be 90, it could be 45, right? Depends upon the situation, and accordingly we will define this vector area. But in general, if we have any angle theta which makes with respect to electric field lines, then the electric flux mathematically defined as a dot product of electric field intensity and vector area, which is shown in equation 11.11. This 11.11 demonstrates is the mathematical demonstration of figure B. Once again, please carefully listen. This 11.11 equation mathematically demonstrates the figure B, and this single equation contains the information about the measurement of electric field, electric flux. So now this single equation contains full information about the electric flux. Means there are what are the factors which affect the electric flux, and what are those quantities which upon which the electric flux is affected. So there are three things. One is electric field intensity, which depends upon the source of electric charge. One is the surface area. Greater the surface area, greater will be the flux. Smaller the surface area, smaller will be the electric flux. And the third most important thing, which is the orientation, that is called angle. Orientation of surface area with respect to electric field intensity. So these three things, this equation contains information about these three things. So look at the beauty of mathematics. Look at that, how much it will be difficult to discuss about that. Electric flux depends upon electric field intensity, surface area, orientation, etc. So all this information I can build in a single equation, and which is in the front of you, represented by 11.11. So electric flux mathematically, symbolically represented by a letter that is called Greek letter, that is called pi, right, with subscript E, where E stands for the electric field, pi stands for the flux, so electric flux, which is equal to E dot A. Okay. So let me check whether our reading is on or off. Okay, so I think so reading is on. So here we have different cases. Flux at any angle theta, he has already discussed at arbitrary angle, maximum flux, and we have another case, zero flux. So the first figure B represents the flux at any angle. So according to that, electric flux is simply equal to E dot A, which is equal to E A cos of theta. And we know from vector analysis from your previous courses, like first year course, we have discussed about the electric flux, about the scalar product and dot product. So dot product is always a scalar quantity. So according, electric flux is a scalar quantity, not a vector quantity. So therefore it should be just a number with proper unit, as we have already discussed in the Zoom. So now the first case, maximum flux. By maximum flux means what should be the situation where the number of field line crossing the vector area is maximum. Okay. So in the first case, if the surface is placed perpendicular to the field such that the surface area is parallel to the electric field E, then the maximum electric line of force will pass through the surface as shown in the figure. When normal to the surface area and electric field lines, which is parallel, then the electric flux will be maximum. Of course, in their situation, the more area is exposed to the electric field lines. So therefore, in their situation, the electric flux, so the cross surface area, will be maximum, right, which is shown in figure C. And consequently, the equation for the maximum electric flux could be equal to electric flux, which is equal to E A cos of theta. Okay, look at that. In the normal to the surface area and electric field intensity are parallel, then the angle between them should be equal to 0. Of course, the angle between two parallel lines is equal to 0. So therefore, when theta is 0, so cos 0 is equal to, from trigonometric expression, so cos 0 is equal to 1. So the mathematical expression for the measurement of the maximum electric flux is simply the product of electric field intensity multiplied by the surface area. So therefore the large number of line pass through the area, right. So this is the maximum, this one is the maximum values. Zero flux or minimum values of electric flux. Zero flux or minimum value of electric flux means ki minimum number of line will be passing across that vector area, right. So geometrically or diagrammatically it is represented by figure D. So in this figure, look at that, the electric field line which is represented by a blue arrowheads, while normal to the surface area is represented by red arrowhead. So look at the angle between both. So the angle between both is totally, which is equal to 90. So if we plug this 90 value in the equation which we have already discussed about the electric flux, which is equal to E A cos of theta. So according to this geometrical interpretation, when angle become 90, then what happened, cos 90 is 0 and this equation reduced to 0. Look at this one, the flux is equal to 0. Okay, this is the mathematical demonstration of the zero flux. But what is meant by the qualitatively demonstration? Okay, look at that, once the surface area is perpendicular to the electric field line, so in that situation less area is exposed to the electric field line. So therefore minimum number of electric field line will be passed across this surface area. So that's why this is the condition for a minimum electric flux. So till to that point we have discussed in the Zoom, but there were only a limited student were present. We have already discussed in detail. Anyway, if you have any question regarding this lecture, this video, this recorded video, regarding any figure, regarding any equation, regarding any case, so you can communicate via Zoom in the next class, inshallah. So I hope you understand and enjoy this lecture, and I'm waiting for your response and for your feedback, how much you have learned and how much you have a problem. So whenever if you have any problem, so you can communicate with me in the next class, inshallah. Thank you very much.